So next lecture is on special properties of compact linear operator on non-linear space. So these are very important properties. So statement of this theorem is let T from n to n be a compact linear operator where n is non-space. Then show that the set of all eigenvalues of T, which is denoted by sigma T, it consisting all eigenvalues, it means it consists all lambda such that T minus lambda I are singular, is countable, it may be finite or empty. And second is lambda equal to 0 is the only limit point of spectrum sigma T. So we have two property here. One is to prove sigma of T is countable. And second, lambda equal to 0 is the only point of accumulation of spectrum sigma T. So these are the property. When T is compact linear operator from same norm space to same norm space n to n, it is a compact linear operator. Clear? So this is very important result and very tough result. So now in the given part, so what is given? Given is T is from n to n. It is a compact linear operator. So first remind the definition of compact linear operator. The definition of compact linear operator, if there is some bounded set M in n, then its image is relatively compact. Its image is relatively compact mean its closure is compact. Clear? So it is a first definition. Second, for every bounded sequence in has, then its image has convergent subsequence. The image of bounded sequence has convergent subsequence. So this is the second definition of compact linear operator. My aim is to prove that this set is countable. What is this? It is eigenvalues. So first of all, I consider a set S. Lambda belongs to sigma t. It means it satisfies this condition. T minus lambda is singular. And absolute value of lambda is greater than equal to k. It means it is not a bounded. It is greater than equal to k for real number k greater than 0. Suppose S is not finite. Suppose S is not finite. Then my aim is if S is not finite, then it means S is infinite. If S is infinite, then it consisting infinite number of element or scalar which satisfy this condition. So it means we can find a sequence in sigma t which satisfy this condition. So by given definition of S, there exists infinite sequence lambda n in sigma t such that absolute value of lambda n greater than equal to k. So that is equation number 2. Clear? Now this lambda n belongs to sigma t. If lambda n belongs to sigma t, then these are eigenvalues. By definition of sigma t, we know that T lambda n, which is equal to lambda n xn. These are the eigenvectors. For some xn does not equal to 0, it means it is a non-zero vectors. Clear? So that is written in equation number 3. Now we take first n vectors. First n vectors x1, x2, x3 and xn. So these are eigenvectors. So we know that the eigenvectors are linear independent. That we already proved in the spectral theorem of previous semester. the set these are eigenvector and eigenvectors are linear independent. So these elements are linear independent. So we take a space Mn which is spanned by these vectors. Now, if we take this Mn which is spanned by this vector x1, x2, xn, then it satisfies both the condition linear independent and spanned by this space. It means these vectors are bases of Mn. Yeah, we may say that Mn has basis of these vectors. Yeah, Mn has basis x1, x2 up to xn. So it means it has n vectors, so dimension is n. Clear? So this Mn is variable. It depends on n. It means Mn has basis of n vector. N minus 1 has basis of n minus vector. And M1 has basis of one vector, M2 has basis of two vectors, and so on. Clear? So this means Mn has basis of these vectors. If this is a basis of this space, then every vector of this space can uniquely expressible as a linear combination of these vectors, right? So for every x belongs to Mn, that has a unique representation. X is equal to alpha 1 x1, alpha 2 x2, alpha n xn, and alpha I are scalar. And this representation is a unique. So that is the definition of basis. That is the property of basis. So that is equation number 4. Clear? Now, t minus lambda n I of x. Now substitute the value of x. So that is a linear combination that we written in this form. Now this is t, first operator t. So this is of this form. And second step minus lambda and I of this. So since t is a linear transformation, so it has property of t of alpha x plus beta y is equal to alpha tx plus beta ty. By using that property, this can be written in this form. Clear? Or similarly, this can be written in this form. Alpha 1 lambda n x1, alpha 2 lambda n x2, and alpha n lambda n xn, because I is an identity operator. So this alpha 1 is common. So from first equations, we get from first equation we get alpha 1 is common, so we get lambda 1 minus lambda n into x1. From second terms we get this equation, and the last term, the nth term, it cancel to each other. This is same term, this is same term, so they cancel to each other. So we get term up to n minus 1, up to n minus 1. Yeah, we get n minus 1 terms. So what is this? Is a first, second, and so on, alpha n minus 1, lambda n minus 1 minus lambda x n minus 1. So these are scalars, these are scalars, these are scalar. So what is this? It is a linear combination of x1, x2, and xn minus 1. So it means it is a linear combination of first n minus 1 vector. If it is a linear combination of first n minus vector, then it means it belongs to span generated by x1, x2, so on xn minus 1. What is this? It is a subspace generated by these vector, which is mn minus 1. So what we get? We get if x belongs to mn, then t minus lambda nix, it belongs to mn minus 1. So what we conclude, if this vector belongs to mn, then t minus lambda nix belongs to mn minus 1. Clear? So one vector less the space with the one less vector. One vector is less than mn. Now, it means t minus lambda I nx equal to mn n minus 1 for every x belongs to mn. So that is equation number 5. Now, dimension of mn is n, and this is less than infinity. If it is less than infinity, we know that every finite dimensional space are complete. If complete, Mn is complete. And then we know that every complete metric space are closed. So Mn is closed. So second we find Mn is closed. So we got two results. One, if x belongs to Mn, then this value belongs to Mn n minus 1. And second, Mn is a closed subspace. Now, this is a Rise lemma that we used in this equation. So, remember these lemma or remember these lemma. To consult these lemma, you can consult any book of functional analysis. Now, what is Rise lemma? Rise lemma is if M and N be a subspace of a norm space X, and suppose M is a proper closed subset of N. This is proper, right? So what do we get? We get total space X, and this is N, right? And M is proper closed. So this condition is proper and closed. Subspace of N, they are subset of N. Then for every real number, that every real number is R. Clear? It belongs to 0 and 1. So lies between 0 and 1. There exists P belongs to N. We can find P belongs to M. Right? This P belongs to M. Norm of P is equal to 1. Number 1. Number 2. P minus M for every element of M is always greater than equal to R. So distance between them is always greater than equal to R for every M belongs to capital M. Right? So this is applicable for proper closed set. R may be any number between 0 and 1. So this is a Rise lemma. That lemma we will use in this theorem by choosing R is equal to 1 by 2, because R is some number belongs to 0, 1. So we take R which is equal to 1 by 2. Now in the given condition, in the given theorem, this Mn minus 1 is a proper closed subspace of Mn, right? So this is treated as N, this is treated as M. So this is Mn minus 1 is proper subset of N. Then by Rise lemma, we get there exists some Pn belongs to bigger set whose norm is 1, and his distance from this set is always greater than equal to 1 by 2, and x belongs to Mn minus 1, right? So that is equation number 6. Now, our claim is to prove this condition. Why? In order to prove this condition, it proves this is not a Cauchy sequence, right? Now, first, I take n is greater than m, then Tpn minus Tpm. So this can be written as lambda n Pn. This is lambda n Pm, right? This is lambda n Pn, and this is Tpm, right? So this is Tpm. Now, by using this result, we add minus lambda n. This can be written in this form. Minus lambda n Pn. One is adding, another is subtracting. Clear? So in this term, lambda n Pn, one is adding and another is subtracting. So this red, the red color is adding and subtracting this term. So we get this values, right? Now from this first term, this is first term as it is. From this we take minus sign out. So this is minus of this number. So what is this number? This is a x bar. What is x bar? X bar is lambda and Pn minus Tpn plus Tpm, right? So we get equation number 7. Now just see. Now this m is less than n. Both are positive integer. It means m is less than equal to n minus 1, right? So by given, if this is less, then this space mm is contained in mn minus 1. Clear? So that is why our choice, that assumption that we used. Also, we know that this pm belongs to mm, and this is subset of this. So this pm belongs to mn minus 1. Clear? So that is equation number 8. Now TPM by definition, this is lambda MPM. It belongs to this, and this is a subspace. So its scalar multiplication is also belongs to this set. So lambda MPM also belongs to Mn minus 1. It means TPM belongs to Mn minus 1, right? So this term that represented as circle, it belongs to Mn minus 1. Remember, this circle term that belongs to TPM Mn minus 1. Right? Now, next part, this square term, the rectangle term. Now, this is lambda Mpn minus Tpn. This can be written as taking minus lambda T minus lambda and I into Pn. So, this can be written in this form. Right? So again, this value, this how we can write this? This is equation number by 5. So this is equation number 5 from the equation number 5, right? So t minus lambda and I x, it is again belongs to mn minus 1, right? So if it belongs to mn minus 1, again this term belongs to mn minus 1. Clear? If it belongs to mn minus 1, then its scalar multiplication is also belongs to mn minus 1. Clear? So this product belongs to this. If this belongs to this, then this term belongs to mn minus 1. This term belongs to mn minus 1. Again, it is a subspace. So x closer belongs to mn minus 1. Right? If x closer belongs to mn minus 1, so this product, this scalar multiplication also belongs to mn minus 1. That is in equation number 11, right? So it means this entire term x bar, this x bar, it belongs to mn minus 1, right? This entire term belongs to mn minus 1. Now, after that, if it belongs to mn minus 1. Now from equation number 7, this equation Tpn, which is equal to, this equation is written in this form. And equation number 7, this is equal to this form. And this can be written as modulus of lambda. We are taking lambda outside, so we get these values. Now this term is greater than equal to 1 by 2 Pn minus lambda n inverse x bar, because this value belongs to mn minus 1. So this product is greater than equal to 1 by 2, and this lambda n is greater than k. So this total product is greater than equal to 1 by 2, this values. Now it means norm of Tpn minus Tpm greater than equal to 1 by 2k. It implies the sequence Tpn has no convergent subsequence. Why? Because it means it is not Cauchy sequence. If it is not Cauchy sequence, even from this, it has no convergent subsequence. If no convergent subsequence, which contradict the compactness of T. So what is the compactness of T? If the sequence has convergent subsequence. So which contradict the compactness of T? It means either S is empty set or finite. If S is empty set or finite, then sigma T is a countable set, right? So sigma T is a countable set. The S is countable, so sigma T is represented in the form of S. So it is a countable set. Also, we can arrange the eigen because this consisting finite elements. So remember, and sequence is in term of infinite terms. It means that any sequence in this set, because it contains finite element, any sequence in this set, it contains finite element, we can arrange the eigenvalues in sequence such that lambda n approaches to 0 as n approaches to infinity, right? Because it consisting finite elements, lambda 1 is 1, lambda 2 is 2, lambda 3 is 3. These are the finite values. So we can arrange the eigenvalue in sequence lambda n such that lambda n, when n approaches to infinity, then it approaches to 0. And why this is possible? Because sigma t is finite. If sigma t is finite, it means 0 is the only point of accumulation of spectrum. In that case, it is a second property. Lambda equal to 0 is the only point of accumulation, the limit point of spectrum sigma t, right? So this is very important result.